Welcome to Session 3 of Ground School USA's Private Pilot Ground School. In this session, we're going to cover the cockpit instrumentation, all the flight instruments that pilots use to determine how fast they're going, how high they are, whether they're going up or down, left or right, and just simply if they're heading in the right direction so that they get to where they're supposed to get. If you've ever seen a cockpit, for example, on an airliner jet, you may have had some oohs and ahs as you looked at all the plethora of gauges and knobs and panels and instrumentation. Or maybe just simply wondered, how can somebody learn what each of those bells and whistles do? Well, those pilots had to start right where we are, with basic flight instruments. And each of the instruments we'll cover in this session can still be found in some form or another on today's airliner jet. First up in the top left, the most important instrument I would say in the cockpit is your airspeed. Your airspeed is incredibly important because everything you do with an airplane, of course, is based on speed. You're flying because you have airspeed. You need a certain amount of airflow over the wings before you can lift off and get off that ground and take off. You'll climb at a certain optimal speed. We'll be talking more about that later on. You'll cruise at a certain speed, and you're going to land at a certain speed. Not too fast and not too slow. The system is called the Pitot static system. Now, why is that? Well, the source of power, what powers these instruments, is the pitot static inputs. Let's look at the pitot first. The pitot, okay, a French word there. You don't pronounce the T there. I always know somebody who's brand new will say pitot. Okay, the Pitot Tube is usually on the left wing, facing right into the wind. Okay, and here's an example of what that looks like. You may have seen this. This is a Cessna, but usually it's some form or another of a tube here protruding into the wind, capturing that what we call ram air pressure, or that dynamic air pressure. The faster we move forward, the more air pressure goes into that tube. Okay, so what will that do? Well, you can imagine that would give some kind of indication to airspeed, wouldn't it? The more air pressure going into the tube goes into the airspeed indicator and will expand our airspeed. Now, we'll talk about how that happens in just a little bit, but that is what we need to know. Now, the airspeed is the only instrument out of these three that are in the pitot static system, okay, that uses the pitot tube, okay, or dynamic air pressure. The rest of them all use static air pressure from our static port. Okay. Now, the static port, I don't have a nice picture to show you, but the static port looks just like that. And it is typically not facing into the wind, but 90 degrees to it. So it doesn't, in other words, get any pressurization from the oncoming wind. We just want the still air pressure. We don't want the dynamic air pressure. We don't want to pressurize that port from moving forward. We just want to find out what is the still air pressure. Now, why would we want to know that? Well, we're going to find out that each of these instruments has a pressure-sensitive wafer inside that expands and contracts with pressure changes. So these are pressure sensitive instruments. Okay, the altimeter and the VSI only use that static or outside still air pressure, but the airspeed uses both. So you can see in this diagram here that the airspeed has got an input from the pitot tube and from the static port. So it's the only one of the three that uses both. But notice before we move on from this slide that we have to have a way of dealing with a situation where we maybe have a clogged pitot tube. The most common clog, for a pitot tube would be ice, and that would be most commonly if you were on an IFR flight. You're an IFR rated pilot. You find yourself in the clouds, that is invisible moisture, with the temperature at or below freezing. If you have those two scenarios going for you, you're very likely to be expecting ice. And it's going to build right up into that pitot tube. So we have a heater, a pitot heat switch that we can turn on, and just that warms up that element and it prevents it from developing. Or you could melt it if you do have ice in the pitot tube. Another thing that we should talk about too is that if the static port became plugged, a little harder because it's not facing right into the wind, but there's a switch inside the cockpit that says alternate static, and if we pull that knob, then we're going to get static air pressure, still air pressure, okay, from the cabin to the instruments. So if I have a problem with my outside static source, I can take the inside static source, and there will be a slight pressure difference between the two, but good enough, and you're up and running again. Let's look at the airspeed indicator in detail. Here's a little kind of cross-section cutaway of the airspeed indicator. So let's look at what this is. The key to this instrument, all three of these instruments, is really this metal wafer. It's an expandable, pressure-sensitive metal wafer. And what happens in the airspeed indicator is, notice we've got the ram air pressure, that's the dynamic air pressure because we're moving forward, moves into the pitot tube, pressurizes, go just directly inside the wafer, and that pressurizes that wafer, or it expands it. It blows it up like a balloon. Just think of it that way, right? And as this balloon, as this wafer expands, it will move from linkages and gears, through linkages and gears, the airspeed needle. Okay, so expands, it's basically going to move the airspeed indicator up, and your airspeed will increase. Now that sounds normal, right? Or that sounds logical. As we would slow down, there's less air pressure going into that metal wafer, and the wafer will collapse or contract, and now we'll register less airspeed. That all works great until we change altitude. Think about that, right? If we all of a sudden go up to a higher altitude, say we cruise up to 5,000 feet. Well, one of the things that we learn in aviation pretty quickly on is that the air pressure changes as you go up and down in the atmosphere. So if you go up, air pressure goes down. If you go down, air pressure goes up. Or we could say the same about the density. As we go up, the density of air molecules is less. The air is thinner. Maybe you've said it or heard it said that way before. Maybe you've gone hiking in the mountains and, you know, wow, I'm really out of breath here. The air is really thin. At least blame it on that. For me, I'm out of shape, but, you know, blame it on the air. So think about if we go up to a higher altitude and we have now thinner air, less air molecules are hitting that pitot tube, are going inside that pitot tube, then we would not blow up that balloon. We would not blow up that metal wafer as much, so it won't expand as far, so we won't register as much airspeed. In other words, we're going to show slower than we are going. So what we have is, to balance that, to kind of create a checks and balances system here, we have, that's where the static air pressure comes in. We have a static air pressure going inside the static line, which is hard to see in this diagram, but that is not going into the wafer. That is going into the casing. Okay, so the static air line is inputted into the casing surrounding the wafer. So now we have kind of two air pressures. One air pressure is in the wafer and one air pressure is out. So what we need to understand there is, then, how does this work? Well, if I'm at a higher altitude, the air is less dense, there's less air pressure going into the metal wafer, which would not expand the wafer as much. However, I also now have equally as well less air pressure in the static line going in the casing around the wafer. So yes, my air pressure inside the wafer decreased, but so did my air pressure outside the wafer in the casing. That decreased as well. So guess what? The net result is basically that the wafer is allowed to expand and register the correct airspeed. Now, the airspeed indicator has color codings, and in and throughout that, we also need to understand this concept of V speeds. V for velocity. Okay, so there's a certain speed at which I need to know something. It can be a limitation. It can be a optimal performance type of airspeed. It could be a recommended landing speed. It could be various things. We're going to look at that, and we're going to look at some popular common V speeds that you need to know about. Next up, we have a pair of performance climb speeds, Vx and Vy. These are really important speeds to know about. Vx and Vy, this diagram kind of shows us the difference. There's an optimal speed at which you climb, assuming your power is fixed. Okay, in a light airplane like the kind that we learn to fly in, it's usually full throttle. Okay, and so that's, you're not really varying the power at all. That's just a fixed amount of power. So what can I vary? Well, I can vary the nose attitude, either a steeper or shallower climb. If I go steeper, I'll go slower. Does that make sense? And if I lower the nose, if I go less steep of a climb, of course, I won't be climbing as good. I'll be a shallower climb out, but I'll also be faster. I'll have more airspeed. So let's look at Vy. Vy is the best rate of climb. That means, assuming again my power is fixed, I'm going to pitch the nose until I reach a certain speed. Again, if I'm too fast, I raise the nose up, I'll go slower. If I'm too slow, I'll pitch the nose down, and I can go faster. So I'm adjusting my airspeed with my pitch. And by getting this optimal speed, which the manufacturer gives us in the Pilot Operating Handbook, we can look that speed up in section 4. In most manuals, it'll be in section 4 of our manual. It'll say best rate of climb. That gives us the most altitude over the shortest time. So, hey, I want to get up to my cruise altitude as quickly as possible. All right, that would be a Vy climb, or a best rate of climb. Rate has to do with time. Now, if I wanted to, if I was more concerned about clearing obstacles, that is, I'm more concerned about something in the horizontal distance, then I'd want to use maybe perhaps the Vx climb, which would be a best angle of climb. And that gives you the best altitude, or the greatest gain of altitude, in the shortest distance, horizontally speaking. So for example, if you had trees to clear at the end of the runway, or some terrain, or some obstacles, antennas, obstructions of sorts, do you see anything wrong with the Vx climb out here, the purple line? Did we not just kind of go through the control tower here? But anyway, the goal would be that I use Vx so that I don't hit the control tower, and I can make it over whatever obstacles, trees, whatever have you, with ease.